All right, let's get started. A couple very, very quick housekeeping items. So we only have one more class after. You're not done with me, so you're still stuck with me next semester. I mean, y'all are taking Engineering 453 at next semester, and if some of you only took one of my design courses, maybe you're taking another, or maybe you're taking hydraulics, or hydrology or pavements or something like that. But you're still stuck with me next semester. I do have a couple quick announcements. First off, if anybody in this room needed another writing intensive credit, I don't know if you saw my email, but you don't anymore, right? Because you should be in project management now, and that's writing intensive, and I just got certified to do writing intensive for Capstone, because it is a writing intensive class. I mean, regardless of what the certification said. So it's like, let's go ahead and make that happen. So Capstone is now writing intensive, and as long as project management is always writing intensive, then civil engineering majors will never need to go outside the major to get their writing intensive credit ever again. I'm sorry.
That was a great English class ago.
I'm sorry. I do a couple other things around. I just didn't get around to it. Let's talk about where we're at in here. This is what I'm thinking of doing. So we have 3 topics left that haven't been quizzed. That's structures, that's prop stats, and then the topic we're going to discuss tonight, which is statics and dynamics. Okay. So what I'm going to do is this. I'm going to let you all off a little easy for a break. You know, we got Thanksgiving and Turkey Day and all that. So when we come back, I think we're going to have 2 quizzes. We're going to have one quiz that's devoted solely to structures, one quiz that's devoted to everything else, prop stats. Because the prop stats questions, I don't think I need 180 questions on prop stats. I can do it in a short amount of questions. And the rest on statics and dynamics, and then we're done. When we come back from break, I would like to meet, because I'd like to potentially get the logistical stuff done for Capstone next semester. Some of the paperwork things, like you all have to submit meeting minutes each week, and company names, and a lot of the sort of logistical stuff that's going to apply to every team regardless of what discipline you're doing, and I'd like to take care of that early so that when we start next semester we can just get right into it. So my structures teams, we can do whatever it is we need to do, and the teams for transportation and multidisciplinary, you all can do what you're going to do, and just that way we can just get started. Our semester is as you know, a week shorter than it normally is, so what I don't want to have happen is, well, it's a week shorter, sucks to be you, because y'all are going to have you're going to have deadlines, and they're going to come up sooner rather than later because of that. So I'm figuring, I still am of the opinion that I still want just a 1 semester Capstone sequence, but since we have 2, I'm going to use this last lecture to handle some of that. Does that sound good? Yes?
Now, for those who are not in the bridge or structure side of the class, will we still be going to your class?
That's a great question, and the short answer is no. Because in the past, this is what I tell. So let's handle a couple of those items now, because I think it's important. So regardless of if you're one of my teams or one of another faculty's teams, here's what I'm going to ask from you in Capstone next semester. I'm going to ask you for weekly progress reports. I'm going to ask you for an alternatives report that's going to have a deadline that is immovable. I'm going to ask for a draft final report that has a deadline that is immovable. I'm going to ask for a final report. That's what I'm asking for. Oh, and team member evaluations. You're going to have those. That's it. There will be points throughout the semester where, take my structures teams, we're not going to meet, because they're going to know what they need to do, and they're going to get it done. You know, I'm going to set. Let me think of the best way. There's going to be a point where I'm not setting the deadlines you are, and so you're going to say, okay, we need to get this done. we don't need to come to class. And that's fine, I don't have a problem with that. But every year, when we get close to alternative report deadlines and whatnot, you know, we don't need to meet. For the teams that aren't my teams, you need to meet with your advisor at least once a week. They're going to tell you what to do. They're going to tell you what needs to be done in order to make sure that you're making forward progress. But they're not going to be, you know, the police saying, oh, you must get this done. You know, a lot of the deadlines in Capstone 2 are being set by yourself, not by me. I mean, there's the report deadlines and the presentation dates, but, I mean, other than that, how you get there is entirely up to you.
So do we like have those meetings with our advisors at the same time you have the class, or do we send
Not necessarily. You all can do it whenever you want. You can find a time that works with your class schedules and with their class schedules, and meet outside their office. You can do, I mean, however you want. So, I know we could probably find space for you. That's not a problem. So, but you can do, yeah. I mean, I remember last year when I had teams working outside of the course with another professor. They were there for the first week. They were there for a couple of days throughout the semester to discuss scheduling logistics with presentations. Never saw them again. Of course, they showed up for the presentation, and I drilled them and all that. But I mean, in all seriousness, that didn't mean they had got it off easy. I can tell you that. They worked. They worked. Any questions? Okay. Statics and dynamics. You want to talk about statics and dynamics? Well, we're talking about statics and dynamics. Okay. So I split this up into two parts: statics and then dynamics. I know, right? Original. So let me explain what my focus is on this review. And let me talk a little bit about this section on the exam. You're going to have what I would call problems like this. This section of the exam is meant to test your understanding of statics. What it is not meant to do is be an IJK cross-product exercise and have you do all this super funky math in order to get the same answer that you could get by just drawing a table and everything going up equals everything going down. That doesn't mean that you're not going to be tested on dot products, cross products, vector, computations, etc. It's going to be on the exam. I guarantee it. Okay. What I'm intending to do with these problems is we've done dot and cross products in our review session this semester before, and we've done. Look, y'all had me for structures. I know you know how to compute support reactions and draw shear moment diagrams and all that stuff. I know you're good. He shaking his head. Yes, he's got me in there. We're good. What I'm trying to do is focus on problems that, everything else, okay? And so when I say everything else, it's going to have sort of a statics vibe, but it's also going to have a physics 211 vibe. I've got, this section on an I-bar, and I've got a bunch of forces. Then I've got a pulley problem. I've got, an overhanging, non-concurrent force system. I've got friction. I've got centroids. This is a type of stuff that we haven't explicitly covered yet, but it's what's left over. So you can think of this sort of as the leftovers review, because that's kind of what it is when you've covered math and structural analysis and all this stuff. Sound good? The other nice thing, and I would say this is true primarily on the static side as opposed to the dynamic side, there hardly aren't any formulas that you need to remember. Okay? Most of this stuff, the sum of forces in the x direction, some trig, Pythagorean theorem, basic stuff. I'll say one other thing. I'm going to spend more time focusing on the statics than I am the dynamics, simply because of the weight on the exam. You civils get 7 to 11 questions on statics, 4 to 6 questions on dynamics. Statics is more important, just period. Okay. What is most nearly the magnitude of the resultant of these forces on this eyeball? This is a very, very typical FE exam problem. A bunch of forces at a common point. This is what's called a concurrent force system. All of the forces all passing through a single point. In this case, the point being the center of the eyeball. So I've got 4 forces. Let's just number them 1, 2, 3, 4. So I'll put that on the screen. 1, 2, 3, 4. And what we're going to do is we're going to start delineating what? Like, how are we going to determine the resultant? Does anybody remember a simple way of doing this? Find your x and y components, add up your x and y components, break out the old Pythagorean theorem. So, force, we have the x component, we have the y component. So let's deal with force 1. What's the x component of force 1?
0.
Big old goose egg. The force or the y component of that force is 10. Now, what I'm going to do is I'm going to make a conscious decision to say that my y components are positive if they're acting upwards. Okay? I think it's a whole lot easier when you're doing these types of problems to just use context. Okay? I mean, you can try and track your signs with your trig functions and whatnot. Just use context. We'll say that positive x is to the right, positive y is upwards. So let's just leave it at that. 2. 15 pounds. Am I going to have a positive x component or a negative x component? Positive y component or negative y component? There we go. This ain't so bad. Now, what I'm going to say is I have 15 pounds times something. Now let's see what that something is. What is that something for the x component? Does anybody know what I would multiply 15 pounds by?
3/5.
3/5, and the y component? There we go. Pretty simple. So I'm actually just going to leave it like that. I'm just going to say 4/5, or sorry, 4/5, and this one's 3/5. Oops, okay. So 3/5 and 4/5. Okay. 20 pounds, number 3. Am I going to have a positive x component or a negative x component? Positive y component or negative y component? There we go. That's positive and that's negative. So 20 pounds times something, 20 pounds times something. What are those somethings? Okay, so 20 pounds times what here for the x component? Cosine of 30 degrees, that one's going to be sine. And then 4, what are the signs for my x and y component? Negative. Negative. So I got negative and negative. And so it's 15 pounds. 15 pounds. For the x component, what's my trig function going to be? The sine of 15 degrees. Remember, the angle's off the y-axis. So when you measure the angle off the y-axis, your trig functions are swapped, right? You know, we always associate cosine with the x and sine with the y, but we swap them when we measure the angle off the y-axis. So let's sum these up. Can somebody say 0 plus 3/5 of this plus 20 pounds times that minus 15 times that? What's the sum for the x column? What's the sum for the y column? Let's do the x column first. Oh, by the way, I did go on Blackboard and upload all the slides for things. It's all current. 22.5. 22.44. Do I have a second on that? 22.44. And then the y component.
Negative 2.49.
Negative 2.49. So, do I have a second on that? So, let me ask you a question. Tell me what to do here on out. Okay. Give me another option that we can do. Circle D. Why? Look at the answers. It can't be A, B, or C because A, B, or C are smaller than these two. The Pythagorean theorem states that their hypotenuse has to be greater than these two. The only one greater than these two is that one. But let's make sure that we did it correctly. So, did that come out to 2.6 pounds? So, when I craft these problems, I sometimes try and ensure that I'm making points throughout the review. And so, remember, the goal is to figure out which choice it is, not necessarily to answer the question. When you looked at your X and Y components, you can look at the choices and see it can't be those. Now you can do the math to ensure that you get the right answer, but remember, the point is to pick one, not necessarily to get it right. I know that seems like a weird statement, but we're trying to pass the exam. You know, we're not trying to prove a point. Something to think about. So always remember, you know, when you're looking at a problem, there are certain points of logic that you should try and enact. Like, are there any answers I can eliminate? Can I do some math and see if some answers don't make sense or what have you? So like, for instance, you know, on that problem, if the answer, or if the question asks instead of what's the result, actually, let's go back to that problem, because I want to make a point. Because this problem could have been made a tad more complicated. Right now, the problem is asking for the resultant, okay? What if the problem asked for the resultant and the direction, okay? So, in which quadrant is the resultant going to be? 1, 2, 3, or 4? We have a positive X and a negative Y. That puts it in the fourth quadrant. Y'all remember that? So if I was graphing 1, 2, 3, 4, so a very common extension to this problem might be, what's most nearly the magnitude of the resultant and the orientation? And so you might have 11.3 and an angle, 22.6 and an angle, 11.3 and an angle, 22.6 and an angle. And so you might only have two resultant values, but you might have different angles as well. And so looking at these two values tells you what quadrant is in. And maybe just knowing what quadrant it's in is enough to recognize what the answer is. And I have another point to make as well. Go ahead.
When they're describing, so like if we did have to look for the orientation or solve for it, do they solve for it from the X going counterclockwise, or do they solve for it going clockwise?
It depends on how it's on how the problem is stated. I mean, typically angles start here and go positive, so a negative angle would go that way, unless it's, you know, like for instance, there's sometimes in kinematics they might say what's the zenith angle, and it's, you know, from the vertical going down. Another point worth making about this problem is look at the magnitudes. I can tell you that the orientation, the resultant's going to be in this quadrant, but is this angle going to be a big angle or a small angle? This angle, so the resultant's probably going to be in this quadrant. It's going to be small, right? Because I'm going over 22.4 and down like 2.49. So it's probably going to be a resultant in the fourth quadrant, and then from the x-axis, it's going to be like 5 or 10 degrees. It's going to be really tiny. So keep that stuff in mind, because maybe that's all you need to know to get the right answer. Don't break out an inverse tangent and do a bunch of calculations if you don't need to, okay? So I know I went a little bit on a tangent. I told my structural analysis students that we have a test coming up in there, and I said, just make sure, like, we had an influence line, so you don't want to be here because then you're under the influence.
They didn't get it, did they?
No, they got it. It's just, it was more of a, it wasn't like, oh, that's funny. It's like, he tried. It was more, you know, just, we'll laugh just to make him feel better, you know. I am a dork. Okay. Okay. So here is a typical problem on the exam. I am curious. I don't want to begin the onset of acute post-traumatic stress disorder or anything like that. But I'm curious, do you all do Pulley problems in statics? Or Pulley problems something that you've been exposed to? Okay. Pulley problems are very possible on the exam. It's not like the exam breaks down to static sections. You'll have a cable problem. You'll have a Pulley problem. You'll have a this. But Pulley problems are very common on the exam because they're a pretty basic breakdown of how statics works. Now, if you have a Pulley problem, does anybody remember how you approach it? Does anybody remember how this works? Okay.
It splits into two T. From like pulleys at a time.
What's that?
You go one pulley at a time.
You go one pulley at a time, okay? And so typically you're going to start at the pulley or at where you're grabbing the rope, okay? So here I've got a series of pulleys, and I'm trying to find the tension that would be applied to pulley A to lift this 1,200 Newton weight. So here's my hand yanking this. How much do I have to yank to counteract this 1,200 Newton weight? So I'm going to start off with pulley A. So if I look at pulley A, so here's pulley A, and I have a rope going like this. So whenever you have a pulley, if this is tension, that's tension as well. It's the same tension throughout the rope. But remember, that's not everything that's going on. There's a rope hung in the middle of that pulley that's suspended. There's a rope hung off that pulley. So what's the tension in this rope?
2T.
2T, there you go, because I got 2T going up, gotta have 2T going down. Then I investigate pulley B. Now, I'm using different colors for a reason. Pulley B has a new rope going around it, but that rope is the rope from A. So maybe what we ought to do is do some colors here on the diagram. Like this is the black rope. This is maybe the red rope. This one, so now let's do the blue rope. The blue rope goes like that, all the way down here, right? Is that a fair statement? And then I've got this green rope here, and I ran out of colors on D. So I only have 4 colors. So we'll say, trust me, it's orange. I don't have an orange. There's no orange button here. There needs to be an orange button, so there's not. Okay. What's that? So here's pulley B. Pulley B has the red rope wrapping around it, and the red rope is experiencing 2T, right? And so the blue rope goes down, that's what's being suspended off that, and so that's experiencing 4T. Make sense? And so then we look at pulley C. And so pulley C's got this 4T, 4T, and so that green rope going down is 8T, right? And you can actually sort of stop right there, because if you look at your 1200 Newton block, what do I have on that? I've got my 8T rope there, and I've got my 4T rope here, right? And so sum of forces in the y direction tells me that 12T has got to equal 1200 newtons. It's not bad, is it? Was it worse?
Much.
I spent 2 months in physics learning that.
You just explained it like 5 minutes.
It's the orange. That's what it was. Your professor didn't have orange markers. You're like, that's it, Dr. Mike.
Which rope has the hats?
Hmm?
Which rope has the hats? I hat. J hat. It's lost.
What?
It's a K hat.
Show read back.
No. No. No.
You lost talking privileges.
I'm sorry. Listen, let me give you my honest take on vectors, okay? Here's Dr. Mike's hot take for those hitting that subscribe button. I think that again, I'm a dork, it's okay. Here's my opinion on vectors just as a whole. I think vectors are very useful when they're useful. Particularly if you're looking at three-dimensional problems. I think they are a really beautiful way of taking a very complex three-dimensional problem and simplifying it into something that's easy to compute. Because you can take a force going that way and a distance that way and easily compute the moment by just r cross f. And that is a significant advantage. But if you're just looking at a 2D system, there is no reason to use them at all, because I think they inhibit learning. Inhibit understanding and inhibit the calculations. Look what we did in structural analysis. I just drew my little box and saying everything going up equals everything going down. And we got the answers far quicker. Okay? So I think that they're a very beautiful way of expressing three-dimensional math. But really in 2 dimensions, I don't think they're all that necessary. So, my hot take. I know, man. You want to talk about a lively comment section that I don't turn on. That's just... I just apparently lost some subscribers, man. You know, they're like, I'm not hitting that bell. Are you kidding me? I don't want to hear that guy ever again. Okay. One truth about the static section on the exam is that more often than not, you are going to experience metric. Okay? The way that the FE exam works is and this is for civils, okay? For civil engineers, the FE exam states that you will have metric on every problem unless, I don't remember the exact wording, but it's sort of like unless it's accepted as an industry standard that US units are appropriate. So one section on the exam I can guarantee that you will use US units is reinforced concrete design. Square root of FC prime, you plug in PSI, you get out PSI. So that will be in US units. Rebar sizes, a number 6 rebar is, the diameter is 6/8 inches, 6/8 or 3/4 of an inch. Everything else is going to be in metric, okay? And that's really important for what I'm about to do with this problem. A sign has a mass of 150 kilograms. The sign is attached on the wall by a hinge here, and I got a cable between point A and point C. What is the tension in the cable? Okay. The reason why I'm mentioning this whole metric thing is because there's a very easy thing to forget on this problem. Statics is an analysis of moments and what? And forces. Forces. That is a mass. Force equals mass times acceleration. It is very easy, this part on the exam, it's very common that you'll get a block that has a given mass and you'll forget to multiply by gravity to turn it into a weight, okay? Don't forget to do that, okay? That's very easy to forget. And it's one of those things where one of these answers might be the answer where you forget to multiply by gravity, okay? And so you'll do the problem thinking, oh, I nailed that one, I got that one right, but you actually got it wrong, okay? So don't forget that. So the weight is mg, which is 150 kilograms times 9.81 meters per second squared. What is that?
1471.
1471.5 newtons. Got a second on that? Okay. So if I look at this from a free body diagram standpoint, here's my box, right? And I essentially have the weight of the sign acting down. I've got a hinge here, bless you, and I've got a cable right here, so we'll say that's going like that because it's in tension. So this is member AC, and we're splitting that up into ACX and ACY. And what I'm going to do, remember, principle of transmissibility states I can take that X and Y component and I can move it up and down along that cable such that, you know, because I can move it up and down as long as those components lie along that cable and I get the same component of moment. So what I'm going to do is I'm going to take that XY component and I can either move it at A or move it at C. I think it would make the problem just as easy. If I move the X and Y component to A, then the Y component will go through this point and then the Y component cancels. Or I can move it down here, X component, and I'm just, or cancels, and I'm just solving for the Y. Yes?
You don't need to know the forces in the hinge B because you can move it between A and C and it will cancel to either one.
Yeah, that's a great point. I actually don't need to know the reaction at B. So if this was a structural analysis problem and we were trying to do shears, moments, whatever, then I could sum moments here to determine the tension in the cable, and then I could say, okay, let's sum forces in the X direction, sum forces in the Y direction to determine what's going on here. But I actually don't really care. All I care about is the tension in the cable. Okay? So what I'll do is let's sum moments at B. So regardless of where I put that force, I'm going to have 71.5 newtons times a moment arm. And how far from B does the weight of that sign act? So the sign's going to caught, like think, if that cable isn't there, that weight's doing that. So it belongs on this side. And how far from B do I place that, or does that result in load act? 2 meters. That's easy. Now, remember, I can take that X and Y component and I can put it here, I can put it here, I can put it here, I can put it anywhere along that cable. I propose that I'm going to put it here. This is ACX, this is ACY. And there's nothing magic about that. I could put it at A2 or at A as well, and I'd get the same answer, but I just picked here. So ACX goes right through it, don't have any moment contribution. ACY times the moment arm as well of 2 meters. So you could look at this and see 1475 or 1471.5 times 2 equals something times 2. What's that something? 1471.5. So ACY is 1471.5 newtons. That's pretty easy. Now, does anybody know the slope ratio for that cable? We go over 2, up 1.5, maybe over 4, up 3. So it's a 3, 4, 5. So if this is a 3, 4, 5, with the vertical being 3, this being 4, that being 5, maybe ACY is to 3 as AC is to 5. Therefore, AC is 5/3 of that, which is what?
2,452.5.
Do I have a second on that?
Yep.
What do you think? Very, very common problem. In fact, I mean, this is really just a moments problem, some forces and some moments. So it's about as basic as it can get. Now, if you want to talk about a problem that I can almost guarantee you're going to have on the exam in some fashion or another, is this. Good old friction. Did you do friction problems in statics? I'm sure you did them in physics, right? You probably had like blocks on an incline and whatnot. You probably had that in physics. Okay, so I got 100 kilogram block resting on an incline. What do I do before I do anything? Wait, I have 100 kilogram block, that's a mass, so I need to multiply that by 9.81 to get 981 newtons. So the block weighs 981 newtons. So the coefficient of static friction between the block and the ramp is 0.2. So remember, we have 2 coefficients of friction. There's a coefficient of static friction and a coefficient of kinetic friction, right? So coefficient of kinetic friction, is it always higher or lower than the coefficient of static friction? Lower, right? That's why when you're pushing a refrigerator across the floor, it's harder to get it started than it is to keep it moving, right? So the mass of the cable is negligible and the pulley at C is frictionless. What is the smallest mass of block B that will start the 100 kilogram block moving up the incline? So we got a block here, keep increasing its weight. How much does that have to weigh, or what's the mass of that block have to be before it starts moving? Now I know the problem's asking for a mass, the block's mass. I still think you just default. If it says kilograms and you're dealing with forces, just convert it to a weight. So weight G, which is 981 newtons. Okay. Now, here's how I'm going to go about this. I need some space, so I am going to draw this out. consider consider a free body diagram of A. Okay? Now, let's see. So here's the incline. Here's the box. So there's box A. Okay. Now, first thing to recognize is we know the weight of box A is 981 newtons. Now, the weight of that box acts downwards. So that's the weight. Okay? Weight always acts in the direction of gravity, regardless what's going on with your incline. Now, speaking of, this incline is at a 3:4 slope ratio. Okay? So, what I propose is that we can take this weight and we can split it up into an X and Y component. Now, the X component, now let me be clear, when I say X and Y component, I'm saying that's X, that's Y. Okay? And so I'm going to use the incline of the ramp to act as my coordinate system. Okay. Now, the weight of A is 981 newtons. I propose that we're going to have a horizontal force component of A and a vertical force component of A. Now, what we're going to do is we're going to take the weight of A and we're going to multiply it by a fraction. And those fractions are going to be 3/5 and 4/5. Okay? Now, what I'm going to do is see how the horizontal component, see how we've got the horizontal component here. The horizontal component here is 4 and 3. Because the angle's flipped, see, our axis goes like that. So that is 3 and 4. So because the axis is flipped, I'm going to say this one is 3/5, this one's 4/5. Now, if that was confusing, why I'm flipping it, I'm going to give you a structural analysis example that makes a whole lot more sense. Do you remember in structural analysis when we had inclined rollers? Remember when we had inclined rollers and the slope ratio was something like 1 to 12, that the reaction was at a 12 to 1. Y'all remember that? So what I'm doing is I'm splitting this up into the X and Y components, but because I'm talking about the perpendicular force, those are going to get flipped. Does that make sense? Make sense? So the horizontal component is going to be 981 newtons times 3/5. This one's going to be 981 newtons times 4/5. So give me the FA, or the HA and the VA. Just help me out.
580.6.
784.8.
Okay. Let me show you where I'm going with this. And if the numbers are, if the numbers aren't really making a lot of sense, I think they will right now. Okay. Let me erase this. This is sort of, I think, maybe an easier way of thinking about it. Okay. Here's a box on an incline. Now that incline is at a 3 to 4. Okay. let's say, for instance, that the incline was 1 to 12. I propose that the weight of that box would be split into two components. One component is going to be a normal force. That's going to push, the box is going to push down on the ramp, and the ramp is going to respond with a normal force acting directly up, right? But there's also a part of that weight that wants to cause it to slide down, right? So here's my phone, here's my arm, and then the farther my arm goes up, the more the phone wants to slide down. The reason why is because as my arm goes up, the X component of that force gets bigger. And once it gets past a certain point, falls down, right? So if I had a ramp that was had a very light slope, the normal force is going to be way bigger than this little dinky force wanting to slide down. Make sense? I propose that at this slope ratio that there is a 588.6 Newton force wanting to cause this block to go down, and that the ramp is responding with a normal force of 784.8 newtons. And the reason why this one is bigger is because that one's bigger. In other words, the ramp is the slope ratio is such that the horizontal component is bigger. Instead of it being like this, it's more like that. Does that make sense? Okay. Now, that's not all. That's not all that's going on. What's also going on is I have a rope pulling this thing up, right? That's what's going on with this problem. There was a ramp, there's a block, and then there's another block pulling it up. Make sense? And ultimately, that's sort of what I'm trying to figure out. I'm trying to figure out what this force is. I'm trying to figure out what that force is that's going to cause that block to start moving. Now, am I forgetting anything? Friction force. Now, if I'm yanking that block up the ramp, friction's going to act opposite of that, right? If I'm pushing a refrigerator across the room, friction's going to hold me back. So if I'm yanking that block up the hill, friction is acting that way, right? Now, what is that friction force?
0.2 times 784.
There we go. So the friction force is the coefficient of static friction times our normal force. And so that is what?
156.96.
Do I have a second on that?
Yep.
All right. So here's sort of what I want to get across. Here's the problem. Here's my phone. Here's my arm. So I've got this at an angle, and I'm trying to yank this phone up my arm. There's two things preventing that from happening. The fact that it's at an angle, the weight of this phone wants to slide down, right? But because I'm yanking it this way, friction is also holding me back as well. Does that make sense? Everybody okay with that? Okay. So if you're okay with that, how do we determine what FB is?
Is it a rotating rotate your axis of the road?
What's that?
Rotate your axis of the road.
Well, just looking at this free body diagram, what would FB be?
Sum of forces.
Sum of forces in the x direction, right? So summing forces in the x direction, I've got 588.6 wanting to push the block down the hill, the weight of the block, and then I've got the friction force acting against the way I'm yanking it. So F sub B is basically just going to be FHA plus FF. In other words, 588.6 plus 156.96, which is what?
735.56.
So this is that. Is that a fair statement? So, what if that force was any bigger than that? Like, what if instead of 745.56, it was 745.57? What would happen? The block would start moving up the hill. What the problem asked, it said, what is the weight required? Like, once you get as fast as it starts moving up the hill. So, is that the answer? Is 745.56 the answer? Divide by gravity. There you go. So, the mass of B is the force of B divided by gravity. So, and that is what?
76.
That one was a hard one. I'll give you that. That one was a hard one. That's probably, I think, the toughest statics problem that you get. So, what do we think? Is that too much? Too little? All right. All right. What's left? What statics concept have I not covered?
Centroids.
Centroids. Exactly right. All right. So, what are the x and y coordinates of the centroid of the area? Now, before I do any math, I would like somebody in this room to comment about the problem and about strategy in particular. I want to see if anybody sees a strategy that we could use to make our lives a little easier.
It's left of center. So where the circle's bigger than the square, but shifted.
Well, that's maybe, but that's not. I'm thinking of something. I'm thinking more of just like test-taking strategies. How do you find the x and y? Hold on. How do you find the x and y coordinates of the centroid? I'm asking. How do you find the x coordinate? Anybody remember how to find the centroid? No. Sum of ax divided by the sum of a, right? Sum of ay divided by the sum of a. Remember? Y'all remember that?
Yes.
Oh, we're gonna have to do some review on that. But all right. Here's I'm leading my question. Look at the points. There's choice A, choice B, choice C, choice D. What can you tell me about all the x values? They're all different. What can you tell me about the y values? They're all different. Just do one of them. That was the point I was making. Don't try and find the stuff. You don't have to find the X and Y coordinates, just find one of them. From a test-taking perspective, that makes the problem half as long.
That's gonna be my downfall. Seeing the simple things like that.
That's okay. That's okay. As long as you can do the problem, that's more important. All right. Everybody with me on this? It's C. You rash. You might be right. I don't know. We'll see. All right. You might be right.
Because the circle's big.
Because the circle's big.
It's going to be back to low, so it has to be C.
Now that's pretty good.
Plus 90% of your answers are C.
That is not true.
It's not I don't know or C though.
That's up to you. All right. My goodness. Break out centroid calculation. All right. So shape 1, shape 2, shape 3. Shape 1 is the rectangular plate. Shape 2 is the circular hole. Shape 3, that's square hole. Have to do a centroid calculation here. Come on now. All right.
Yeah, everyone is happy for deform, and I don't think everyone teaches it so easily.
All right. So we got 3 shapes. Thank you. No. Shape 1, shape 2, shape 3. First thing we're going to do is we're going to write some areas. So somebody help me out. What is the area of shape number 1? Shape number 1 being the area of this whole plate. It is 8 centimeters wide, 10 centimeters tall, 80 square centimeters. That is exactly right. Let's talk about that circular hole. What is the area of a circle with a diameter of 4 centimeters? Pi d squared over 4. 4 pi, which is? Got calculators.
12.57.
12.57. Now watch this. 12.57, we'll stick a big old negative on that. It's a hole. Cut. What's the area of a square that's 2 by 2?
Cassie, make sure they haven't changed anything on me though. They haven't changed math for anything, have they?
All right. Pick your poison. You want to do X or Y?
X.
X. X. So, the way this works, you got to pick a data, a point of reference. Fortunately for this problem, they've already done that. Right here. So this is my point of reference. Call that the datum. Now, where is the centroid of the rectangular plate from the datum? Now we're talking, you said X, so we're talking about horizontal distance. From here, how far do I have to go over to get to the centroid of that rectangular plate? 4. Exactly right. Now how far do I have to go over to get to the center of that circular hole? 5. Big old 5. How far over do I have to go to get to the center of that square hole? 2. There we go. So, does anybody remember that the centroid is computed as the sum of AX over the sum of A? Does that formula look familiar? So we need the sum of A's. Those are pretty easy. What is the sum of the A values? Everybody got them? 80 minus 12.757 minus 4?
63.43.
The next thing that we need is an AX column. And so how do we do that? Bam times bam, bam times bam, bam times bam. So 80 times 4, that was 320. I don't know that middle one, but the last one, that's minus 8. All right, make that a little better.
62.85.
So sum that up, what do you get? So 249.15 cubic centimeters over 63.43 square centimeters is what?
3.92.
3.92. Do I have a second on that?
0.93.
0.93.
I think, maybe I'm going crazy, but I think, I mean, obviously you didn't teach statics or dynamics to us, but the nomenclature that we used in class, I think it was y-bar, it was always the opposite. It was like y-bar is like the distance from the y-axis over, was how we referred to it on the homeworks. So like whenever you,
it was an x distance.
it was like,
y bar, x bar was like a y distance.
yeah, so we're looking for like the x coordinate, you look at it from the y-axis, so it was always y-bar.
It was more confusing than it had to be.
Yeah.
Here's what I'm going to do.
My question
What-
is
what-
this how they do it on the exam?
Watch this. Okay. There's a magic point right here, and I'm going to say it's x comma y. I'm not trying to be smart, I'm being serious. Like,
I just remember for some reason it was really weird.
It was always the
Like,
opposite of.
So, like,
That's why.
when I measure, I'm really not trying to be facetious, but when I measure distances this way, I kind of call them x's. So when I measure distances this way, I call them y's.
Makes sense. So I was taking deep with you.
He was trying to
And I was taking
really
dynamics at the same time.
push the point that it was from the y bar was the x.
From the
He
y
just did it
axis.
really, yeah. From
But
the
that's true. And
Yeah.
then
He just
from
did it confusingly.
x, well, I mean, yeah, you're measuring, yeah, whenever you're graphing things, like the coordinates of the point 2 comma 3, how do you get the 2? You start at the y-axis, you go over 2, you know? That's true, I mean, that's, yeah. I don't have anything else to say. Now, let me be clear. So that is how you locate the centroid in terms of the x-coordinate. Now, this is what I was saying when you go back to the problem. If you go back to the problem, see, all of the choices are independent. So by doing this one, I don't have to do the y-coordinate. I know that's the answer. Now, if you would like, what you could do is set up a completely separate table, do this again, only instead of 4, 5, and 2, what are the numbers going to be for the y-coordinates? Well, how far is it from the datum to the center of the plate, up and down? 5. How about to the circular hole? 7. And this is going to be 2. So do this problem all over again, only instead of 4, 5, and 2, use 5, 7, and 2. And what will happen is the denominator will be exactly the same, but the numerator will be different because you multiply by different distances. Notice how the values are larger. Instead of 4, 5, and 2, 5, 7, and 2. So because it's 5, 7, and 2, this answer is going to be larger than 3.93. I didn't do any math, any calculations or computations to see that. But look at the answer. The answer is 4.79. I guarantee it's 4.79. What do we think? Should I throw in an IJK just for the hell of it?
Sure.
I'm not.
Review the right hand thumb.
Any questions? All right. That's all I've got for statics. I'm going to to do some very, very basic dynamics problems. Okay, let me be crystal clear. The dynamics that you get on the exam is just that, basic, okay? Your civil engineers. Generally, our stuff doesn't move, right? The old joke, or mechanical engineers design weapons, civil engineers design targets, right? So, you will get assessed dynamics problems, but they usually are pretty basic. A lot of particle motion, a lot of rectilinear stuff, very little curvilinear stuff, and I think I'm only going to do like 3 problems, because I don't want to keep you here too long. Anyways. Okay. A particle starting from rest experienced an acceleration of 3 meters per second squared for 2 seconds. The particle then returned to rest in an additional distance of 8 meters. Assuming all accelerations were uniform, what was the total elapsed time for the particle's motion? So how long did it take for the particle to start and then stop? So the way that I handle this is I look at this as if there were 2 problems, right? The 2 problems being I have motion number 1, or maybe motion number 1, action number 1, whatever you want to call it, and then I have action 2. Let's look at action number 1. So I have a particle starting from rest. What does that mean, starting from rest? Its initial velocity is 0, and it experienced an acceleration of 3 meters per second for 2 seconds. So it has an initial velocity of 0. What's its final velocity? Well, you're exactly right. It will be 6, and we'll see why, but right now it's unknown. The acceleration, 3 meters per second squared for a time of 2 seconds. Now, here's the thing. The problem is asking for the total time elapsed. Total time elapsed. I already know how long action number 1 took. How long did it take? It took 2 seconds. So you might think, why do I even need to do anything with action number 1? Why don't I just move on to action number 2? Let's see what we know about action number 2. The particle then returned to rest in an additional distance of 8 meters. Okay? So, hold on. What do we know about action number 2? Well, I have no idea what the initial velocity is, but we'll get to that here in a second. I know that the final velocity is 0. I don't know what the acceleration is. I do know that the distance was 8 meters, and I don't know what the time is. So, initially, you might think, I don't need to do anything with action number 1. I already know it took 2 seconds. But, based off the conditions of this problem, I propose that the final velocity here is the initial velocity there. Right? So, let's find that final velocity. And I propose that we determine final velocities by taking our initial velocities and adding acceleration times time. And so that's 0 meters per second plus 3 meters per second squared. Sorry. And then 2 seconds, so...
We didn't need to know any formulas.
Oh, I said for statics, I didn't say for dynamics.
Yeah, that's true.
But yes,
I
it
was
is
just
in
gonna
the
have time.
I'll have to check the recording. That's 6 meters per second. And I propose that that 6 meters per second is the same as that 6 meters per second. All right. But I did say for statics. No, I'm not. I gotta make it entertaining. I mean, it's like the Wednesday before Thanksgiving. It's 5 o'clock at night. You're like, okay, come on, get on with it. All right. So I've got a final velocity, an initial velocity, and a distance. Let's see. Do y'all remember this old ditty?
Are the kinematic equations in the test?
Yes, there. Yes.
So states of the accelerations were uniform, so how we also know what it is for action 2 then?
No, we know that what that means is that the acceleration didn't change throughout that motion. Acceleration could theoretically be a function of x. What this is saying is, so remember how we relate position, velocity, acceleration, right? The derivative of position is velocity. The second derivative of position is acceleration. So when you first start deriving these equations, you say, well, if acceleration is constant, I integrate that to get velocity. I integrate that again to get position, okay? So, but in order to derive it, you have to assume acceleration is constant. And that's what that's saying in action 2, is that the acceleration is constant. Like gravity. Gravity is a constant. It's a number. All of our, weight equals mass times gravity and all of that is all based off of that concept. That's a very fair question. Does that sound good? All right. So Vf squared equals Vi squared plus 2ax. So I can use this to determine the acceleration. And so what is that? 6 squared is 36 over 16. 36 divided by 16 is what? Negative 2.25 meters per second squared. Does it make sense that it's negative? Why? It's slowing down. Yeah, it's decelerating, so it's negative. So if I have now the acceleration at negative 2.25 meters per second squared, maybe I can break out that original formula that the final velocity equals the initial velocity plus AT, and I can say that the time elapsed is the final velocity minus the initial velocity, all divided by the acceleration, which is what? Remember, one check is that your time usually has got to be positive. Huey Lewis going to get back anytime. Back to the Future. Come on. What do we got?
2.67 seconds.
2.67 seconds. So that, right?
No.
No. That. What's the problem asking? The problem's asking for the total time elapsed for the two motions, right? It's very easy on problems like this. Oh, hey, no, it's not. It's C, okay? Because you have to add the 2 seconds from the initial action. Don't forget stuff like that. I'm being serious. You're taking an exam, you've been in there for 6 hours, this is easy to miss. So, sound good? All right. I like this problem. All right. A 550 kilogram mass initially at rest is acted upon by a force expressed by this function. What is the displacement of the mass at t equals 4 seconds? So I have, let's think about this. So I have a force, I have a mass. If I have a force and a mass, what can that tell me? There we go. Force is 50 e to the t. Mass is 550. So acceleration is F over m. So 50 e to the t over 550. So e to the t over 11. Now the problem's asking for what is the displacement of the mass at t equals 4 seconds. Now I got a function for the acceleration. How do I do that? Tell you what, let me ask you a different question. I have the acceleration. I have a function that describes the acceleration. If I have a function that describes the acceleration, how do I develop a function that describes the velocity? You integrate it, right? Because the acceleration is defined as the derivative of the velocity. So if I've got the acceleration and I want to find the velocity, I integrate, right? So therefore, the velocity is the integral of e to the t over 11 dt. And so what is that? What's the integral of e to the t? E to the t, right? And so what's the integral of e to the t times a constant? E to the t times a constant. So this is the integral, right? E to the t over 11 plus c. So we'll call that C1. How do I determine C1? Say it again. Boundary conditions. This particle started at what?
Rest.
At rest. So what is a boundary condition that will help me solve for C1? Say it again. V equals 0 at what? At
T equals 0.
There we go. At t equals 0, v equals 0. So v is e to the t over 11 plus c1. 0 equals e to the 0 over 11 plus c1. What is e to the 0? 1. So 0 equals 1 over 11 plus c1. C1 is minus 1 over 11. What do you think? Not too bad. So V is e to the t over 11 minus 1 over 11. Now that'll tell us the velocity of this particle at any particular point in time. I don't care about that though. What I care about is the displacement of this particle at any particular point in time. So if I have a function for the velocity, how do I determine a function for the displacement? Integrate it again. So therefore, the function for x is the integral of e to the t over 11, bless you, minus 1 over 11 dt. And so what is that integral going to be? Oh, hold on. One, you tell me. So the integral of this part is just integral of this part. Well, t. Yeah. And then plus c. There we go. So we've got e to the t over 11 minus t over 11 plus c2. And then now we got another boundary condition, right? And that other boundary condition states that at t equals 0, so at t equals 0, x equals 0. Because that's what at rest means. 0 displacement, 0 velocity. So x equals e to the t over 11 minus t over 11 plus c2. 0 equals e to the 0 over 11 minus 0 over 11 plus c2. So what's c2? negative 1 over 11. So x equals e to the t over 11 minus t over 11 minus 1 over 11. And so how do I solve the problem? How do I determine the answer? Plug in t equals, and if you plug in t equals 4, you get a value of what? $4.51. Do I have a second on that? Pretty straightforward, isn't it? Okay, we got time for one more, and then I'm just going to call it. All right, so first off, though, I don't want to, oh, I didn't mean to do that. I don't want to skip ahead. Does anybody have any questions? Yes, sir.
So both of these have been kind of kinematics related. So there were like 3 defined sections in dynamics. It was like kinematics, then energy, and then I guess the last part was like rotational or.
So I've got a momentum problem here. This is a momentum problem that I'm about to do. The next one's rotation, and I have a centripetal problem here, but I don't think we're going to get to it in time. I might record it.
Are there bits from all 3 of those on there? Because the third section did like incredibly that might have just been class. Like
What?
I remember like the third portion of the class, like first you kinematics and energy. The third portion being like
Oh, the rotation stuff being hard.
being like really in depth and like.
Yeah, I know what you're talking about. I remember when I took dynamics that the rotation part in the course was just, but the stuff that you get on the exam is very, very simple. Like you have a ball on a string, what's the centripetal, acceleration, like the v squared over r stuff, like to just plug and chug basic stuff. If you're good at that stuff, and I'm being a little facetious here, but civil engineers really don't deal with it that much. The only dynamics that we ever really deal with in our actual careers are the very basic particle motion stuff, because I think it's important from a fluid standpoint and from just a motion and transportation standpoint. And then we deal with vibrations. Did y'all do vibrations in dynamics? Like mass spring?
That was more. We did that.
You did do mass spring? Okay, because mass spring damper is how we do earthquakes, how we handle earthquakes. Because that's how we treat a building. It's mass, spring is its stiffness, and then dampers friction and all that stuff. And so if an earthquake hits it, what's its acceleration? All right. This is my momentum problem, and then I'm going to let y'all out. Because I do have one final problem, but it really is just like a v squared over r. It's really simple. So I got a 2 kilogram ball of clay moving at 40 meters per second, and it collides with a 5 kilogram ball of clay moving directly towards the first ball with a velocity of 10 meters per second. What is the final velocity if both balls stick together after the collision? Okay, so this is, in a nutshell, a momentum problem. Okay, so a conservation of momentum, so conservation of energy, conservation of momentum. So let me ask you this. Does anybody remember how we define momentum? Mass times the velocity, right? So what we're going to have is we're going to have a ball of clay. So ball 1, ball 2, colliding with one another. This is what it's like in worlds below. Right? So the mass of this one is 2 kilograms. The velocity of this one is 40 meters per second. Okay? The mass of this one is 5 kilograms, and the velocity is 10 meters per second. Now, here's the thing. They're acting in opposite directions, so you got to pick one to change the sign. So typically what I would do is I would just say anything going to the right is positive, anything going to the left is negative. So we're going to say this has a negative velocity because it's acting in the opposite direction. Okay? So I propose that the total initial momentum is m1v1 plus m2v2. And so that is 2 times 40 is 80, 5 times 10 is 50, 80 minus 50 is 30 kilograms times meters per second. So that's the total momentum in the system initially. Because I got 2 going at 40, 5 going at 10, and they're going in opposite directions, so I take the difference. Okay? So that is the initial momentum. The final momentum has to equal that. So the system has 30 kilograms times meters per second momentum at the beginning. It's got to have 30 kilograms times meters per second at the end. Now, I don't know the final velocity, but I do know the final mass. What's the final mass of the system? 7 kilograms, because there are 2 balls at play and they stick together. So the final mass is m1 plus m2, which is 7 kilograms. So therefore, if mv initial has to equal mv final, the final velocity is mv. This pen sometimes cuts out. mv initial over m final, which is 30 kilograms meters per second over 7 kilograms. So 30 over 7, what is that? 4.29 meters per second. Okay. We could probably do the next problem. Now the next problem, it actually does require a tiny bit of derivation. They used to report this formula directly in the manual, but they've since changed that. But I might just post a quick solution on that later. It's getting kind of late, and I think that problem might take a little bit longer. I don't think it's all that necessary, and I don't want to keep you here any longer week before Thanksgiving. I'm going to put you through the ringer next semester anyways. I'll give you a break. So enjoy your turkey or turkey substitutes if you enjoy plant-based diets. He didn't hear that. Did you like? Are you going to go with a plant-based substitute for turkey?
Yeah.
Your laptop gave it away. All right, that's all I got. We'll see y'all after break.